Hey, how's it going, Jeff?
I'm going to use my laptop speaker because my laptop microphone because my USB microphone doesn't seem to be working right now. All right, so once you're back and ready, we can start.
Yeah, no problems, man. That sucks about your mic, though.
Yeah, is the laptop mic okay though? Can you hear me fine with that?
Yeah, no, I can hear you pretty clear with that. Yeah.
Okay, good. Excellent. All right. Um, so for those of you joining us this evening, I see we have a couple viewers already, Andrew Eddy, and a couple others, I'm sure. My name is Jeff Pinion, and I'm talking to Josh Walker. Josh lives out in California, and I live out in Jersey. And we're going to have another civil and calm and reasoned discussion about the universe and the Earth and observations we can make, things we can know. And I know one of the topics that Josh wants to talk tonight about is gravity. It was something we talked about in our first conversation, probably about 2 months ago. I think it was the beginning of April that we had our last conversation. And I know we talked about gravity for a good long while. And I think one of the things we ended up saying was, or one of the things I ended up saying was that I wanted to look into Newton's Principia to try and find where Newton actually gives his definition or his description of the force of gravitation, because the equation that we see in textbooks of force equals G times big M times little m divided by r squared, Newton never wrote that. And as Josh points out correctly, Newton didn't know what G was. Newton didn't know what the universal gravitational constant was. But what Newton did write in his Principia, and I can pull this up later as we talk about it more. What Newton did write is that this force of gravitation or this force of attraction between two spheres of mass, he said that that force is proportional to the inverse of the square of the distance between them, and it is also proportional to the product of their masses. So that's Newton's way of saying that gravity, the force of gravity between two objects, is the mass of one times the mass of the other divided by the distance between them squared, and then something else. And he didn't know for sure what the the rate of that proportion was, but he knew that proportion was there. And so that was one of the things we ended up last time, was that I was going to look into that and try to find it. And so I guess I've been talking for 2 straight minutes, so now I'll let Josh do his little introduction while I pull up Newton's Principia. So Josh, you can go ahead and make whatever beginning remarks you'd like to.
Thank you, man. And pleasure talking to you again, bro. It was fun last time, so figured why not do it again, right?
Good, good.
But yeah, no, I also downloaded the PDF of how are you pronounced Principia? Is that
It could be pronounced Principia or Principia. When I pronounce Latin, I tend to pronounce CIs as chuz rather than as cuz. So Principia.
okay? Because I was pronouncing it Principia, kind of like is I thought I was for some reason maybe I should have looked it up, but Principia I thought was like principles
Well,
in Latin.
right, right. The English pronunciation, when we say that word, we would say principle. There's a lot of questions about how Latin is actually supposed to be pronounced, like classical Latin versus ancient Latin. And so it could be Principia, Principia. It probably
Gotcha.
wasn't Principia. It probably wasn't a soft C. But pronunciation aside, uh, we both decided to look at the source as much of the source as we could. Obviously, we didn't read it in Latin. We ended up both going to English translations.
Wasn't even going to attempt the Latin. I don't know you, but I wasn't going to go through that. That would have been a nightmare, considering the fact that it's a dead language. Wait, yeah, Latin is a dead language, right?
Right, and that's one of the things that makes it useful, is because as its meaning isn't supposed to change because it's dead. Anyway,
Yeah, gotcha. But yeah, no. Let's see. There was his Principia, and then there was what else was there? Yeah, I've been digging into a whole bunch of stuff since the last time we talked. Uh, as a matter of fact, I found out about Echo One. Echo One's really fun.
yeah, you mentioned. I don't know if you mentioned it for sure in our last conversation, but I know I heard follow up with you. You are very interested in Echo One, so we can talk about that tonight as well.
That yeah, because that just that one kind of throws me for a loop. And I was talking to a guy a couple weeks ago, and his whole answer after everything I told him was, "Well, it must be possible because they did it." But that's like thinking backwards, though, right? Like, I mean, if you're trying to prove that you did something and you just tell someone you did it, that's not proof that it can actually happen if there's no demonstrable like example of it, you know? Like
Right.
there's no
It's more or less begging the question, like, if, for example, we're talking about flat Earth versus globe Earth, if somebody were to say, show me water conforming to, show me, show me water conforming to the surface of a sphere, and a globe Earth person said, well, the Earth, that that seems like a cheap argument, because it's the very question of, can water stick to the surface of the earth if the earth is a sphere? Like, that's the whole matter of contention. So you can't use the thing that's the matter of contention as your argument or as your proof. So yeah, I understand, like, when we're making these arguments, or when we're trying to determine the veracity or the truthfulness of a claim, it's kind of circular logic to simply say, well, this thing was claimed to have been done, so clearly it's possible. But yeah, so go on.
Yeah, it's a lot like trying to use the word in the definition, right? We were all taught we're not supposed to do that.
Exactly.
But yeah, let's see. I just got home right now and I'm downstairs. I'm not even up with my computer right now. Um, if you can give me like 5 minutes to get upstairs, and then we can really get this kicking. All right. But yeah, dude. Did you happen to catch the Russian launch today though? It wasn't too bad. Although I think NASA puts out better. I think NASA's got better cartoons though. Opinion. uh, and I mean, we all have to admit when we're watching that footage, like at a certain point when the rocket goes up, we all have to admit they switch to cartoons. Like it's where they show the rocket separating and stuff like that. Like it looks like a rendered video from like AutoCAD or something. Like it's completely graphic, and I don't know. That's one of the issues I have is if it can be done, where's the real footage for it? Uh, but yeah, uh, give me a second to finish what I'm doing down here, and I'll get upstairs real quick. All right.
People in YouTube, can you hear me now? I think I was able to hear myself in the video. Okay. So sorry about that audio problem. I don't think I got sniped. I don't think I got muted. Um, so I don't think you missed too much there. I was just saying that I hadn't seen the Russian launch today. I had seen a previous SpaceX launch where they released satellites at one altitude and then went further up into the atmosphere or up into space and then released more satellites. Um, Let me see if I can pull up on YouTube the most recent SpaceX launch video. Just because I would like to consider, I guess it was the Iridium 6 launch, maybe 2 weeks ago. That seems a little long ago. Um, but
That sounds like the Bangladesh launch.
all right, let me see if I can queue up one of these videos to where the where there's a detachment. Okay, I think that's it. So let me bring this over here and let me share my screen. Screen one, Present to everyone. All right. So this is Falcon 9 carrying SES-12. So I'm not sure if this is actually the most recent one that I watched, but this is just a bit of the video clip of the launch. So this is the rocket going up, and in a moment they're going to do main engine cutoff, I believe. Right. So this is the sort of footage I'm familiar with seeing when they do the detachment of one part of the rocket from another. I will admit that there are parts of the SpaceX video where they will then cut to what is obviously an animation showing you like the trajectory that the rocket is going to take around the Earth. But I don't consider what I'm watching right now to be animation. Like this whole thing that we've been watching over the past minute or so, I don't see any reason to believe that this is a computer animation. This looks authentic to me.
Yeah, no, I agree that that is an actual object sitting there. But I wouldn't say that it's floating anywhere. That's all. Uh, but that's just me. Um, oh wait, I remember this one because when I first saw it, I was tripping out the fact that the rocket was burning purple.
That could simply be an artifact of the camera being used at the time. I'm
That's what I chalked it up to. That's why I didn't really, push it. It bugs me when I see people reaching for things to try to use as evidence and examples and proofs. I don't like that. I want something that just about anybody can look at and be like, oh, duh, okay, I see that. I don't want to have to like push them through a bunch of hoops to get them to where I'm trying to explain something to them. Simplicity. Uh, Occam's razor, right? Yeah.
mhm. All right. So would we like to get into gravity then?
Yes.
All right. Let me stop the screen share. All right. So I'll let you start, and I'll jump in as I see fit. But you can take the floor for now.
All right. Mind if we start with a little fun thought experiment real quick
Sure.
regarding
Go
gravity?
ahead. Sure.
Okay. So if me and you are hanging out in my backyard, right? And
Hmm.
I'm on one side of my yard and you're on the other, and I'm standing in front of a barrel, right?
Hmm.
From across the yard, can you tell me what the mass of the barrel is?
No.
Can you think of an example where you can look at something and tell the mass of it, though? Just by looking at it by itself, just it.
Probably not. I don't think just by looking at an object, especially at an object stationary on the ground, I don't think I'd be able to have a good idea of what its mass is.
So when we look up at the moon, right? How do we tell, like, the thinking of Newton's equation with M1 and M2? that stands for the mass of the first object and the mass of the second object, right?
Hmm.
So isn't that assuming that you know the mass of those objects to be able to work that equation?
Okay, right. So what this comes down to is how do we know the mass of the Earth, first of all? And second, how can we know the mass of the moon? So the question of how do we know the mass of the Earth, that's a question I don't know the answer to offhand, and I'm going to Google it right now. How do we know the mass of the Earth? Okay, so the first hit that comes up is from Scientific American, and let's see. Because we know the radius of the Earth, it says, we can use the law of universal gravitation to calculate the mass of the Earth in terms of the gravitational force on an object at the Earth's surface, using the radius of the Earth as the distance. This requires the constant g. But I have a feeling that this is a bit of circular reasoning because, first of all, this is assuming the Earth is a sphere, and then it's assuming the law of universal gravitation. So let's look at this a slightly different way. When Newton was devising his law of universal gravitation, what he was attempting to do was establish what laws the universe acts by, which can explain the perceived motions of not just the celestial bodies, but also things on Earth in general. So, for example, his law of universal gravitation explains not only why an apple falls from a tree at an acceleration of 9.8 meters per second squared, but also why the moon orbits the Earth in the amount of time it does, and why the Earth orbits the sun in the amount of time that it does. Now, in all of these cases, Charlie in chat is saying the mass of the Earth was initially determined by the Cavendish experiment. So I think what Charlie is saying, and Charlie, you can continue in the chat if I have you mistaken. Basically, so the Cavendish experiment, by determining what the gravitational constant is, they were then able to use the gravitational constant to figure out what the mass of the Earth must be in order to produce a gravitational acceleration on Earth of 9.81 meters per second squared. Charlie, if that's right, you can say yes. If that's wrong, you can give me a correction. But so, continuing on, in your thought, go ahead.
Even if you know the size, right? Like with the whole barrel idea, right? The barrel is the same size no matter what. But what if it's filled with concrete?
Right.
Or it could be empty. Remember, okay, in the email I sent you, I told you it was going to be a barrel of laughs, I promise. That's because I was planning on asking you what was in the barrel.
So the difference between your thought experiment and the sorts of experiments that Galileo and Newton did is that in your experiment, you and I and the barrel are essentially inert. We're not moving. You're at one end of your yard, I'm at the other end of your yard, and there's a barrel somewhere between us. And we cannot perceive in any way a force that the barrel is exerting on you, or that you're exerting on the barrel, or that I'm exerting on the barrel, or that the barrel is exerting a force on me. We can't detect any of that. The difference is that in Galileo's experiments, first of all, okay, he had an object of a known mass, and he was rolling a marble essentially down a ramp. Okay, but the key there is that he didn't even need to know the marble's mass, because he found out that the acceleration on Earth doesn't matter what the mass of an individual object is. He had marbles of different weights rolling them down a ramp. They all moved with the same acceleration. So in his case, he was using a moving barrel. Okay, he was using a moving barrel, and he ended up not knowing or not needing to know what the mass was, but he was able to determine the acceleration of that object. Now, none of this answers the question of, well, what's the mass of the barrel or what's the mass of the marble? Because again, when we're dealing with experimentation and measurements and calculations, I don't need to know what the mass of the Earth is, and I don't need to know what the radius of the Earth is, and I don't need to know what the mass of this mostly empty beer bottle that I have in my hand is. If I were to make a video recording with a slow-mo camera of me dropping something like this beer bottle from my desk to the floor, I can know how far it fell, and I can know how long it took to fall, and I can, using my high-speed camera or my slow-motion camera, I can track how far it went after 1 second, after 2 seconds, after 3 seconds. And using that data, I can calculate the acceleration of the beer bottle. And I did this without knowing the mass of the Earth, without knowing the radius of the Earth. The only thing I know, really, is the height of the desk and how long it took the bottle to fall. Using those two pieces of data, I can figure out, okay, the bottle fell with an acceleration of 9.81 meters per second squared. It's so, as people in chat are saying, it was when Cavendish's experiment took place and he was able to determine that this attractive force which exists, he was able to figure out not only that attractive force is proportional to two masses and to the distance between the two masses, but then he was able to determine exactly what factor you need to multiply one mass by the other when you divide by r squared. He was able to figure out what the constant is that makes the proportionality into an actual equation. And with that information, once we know what the universal gravitational constant is, then we can say, okay, if the force of gravity is this constant times the product of two masses divided by the radius of the distance between them, if I know that the acceleration of an object when I drop it on Earth is 9.81 meters per second squared, and I know that force equals mass times acceleration, then that means that the gravitational constant times the mass of the Earth divided by the radius of the Earth squared, that value has to equal 9.81 meters per second squared. You need to know either the radius of the Earth or the mass of the Earth in order to figure out the other part of that. If you know the radius, then you can determine the mass. And if you know the mass, you can determine the radius. So,
if you just because you can determine the radius, though, it doesn't mean you can determine the mass, because you need to know what's inside of that radius. I mean, if the Earth is filled with helium, which, I mean, we're pretty sure that it's not, but if let's just say that it was, then wouldn't the mass of the Earth be much different than what we think it is now?
Yes, and if the Earth were filled with helium, the force of gravitation on Earth would not be 9.81 meters per second squared.
How do you know?
Because force equals mass times acceleration, and we know that the acceleration on Earth is 9.81 meters per second squared.
Have you ever heard of a gentleman by the name of Coulomb?
Like Coulomb's laws and all that?
Yeah.
Yeah.
Have you ever looked, like, when was the last time you actually like looked at Coulomb's law? Because
Uh,
I
high
came
school
I came across
physics.
this again just the other day, looking through this stuff, and I've been doing some research on the Eiffel Tower. Actually, there's 72 names on the Eiffel Tower, and there's some pretty prominent names, like Mr. Coriolis is up there with the Coriolis effect. Foucault is on the Eiffel Tower. Dumas, who's responsible for the periodic table. Let's see who else. You've heard of Lagrange points, right?
Yeah.
Lagrange is on there. Uh, there's a ton of people on there. There's a guy on there. I didn't realize this. Have you ever heard about Edmund Halley's calculations for his comet? Did you know that they were off originally? They actually had to be corrected by somebody.
That wouldn't really surprise me. A lot of the earlier astronomical calculations have had to be revised.
But yeah, here, okay. Let me get off my phone real quick. My computer finally turned on. It's being nice, so here, let me swap devices really quick. Give me 2 seconds. Here we go. Am I back? Can you hear me?
Yep.
What happened to my sound?
I can still hear you.
All right, let's see. Just fix it. This is all right. There we go. I got sound now. Awesome. Now let's screen share. Let's wait till it stops flipping out. Cool. All right. Let's see. When I came across Mr. Coulomb's his equation for calculating electromagnetics, I thought it was interesting because it it looks so much like that is almost the exact same setup as Newton's equation for gravity.
Right. Some constant times one charge times the second charge divided by the square of the distance between the charges.
Well, we know that we're electrically charged. We know the Earth is electrically charged.
The primary difference between the law of gravitation and the law of electromagnetic or Coulomb's law, essentially, as you'll see from the end of the first paragraph there, Coulomb's law, the force of interaction can be attractive or repulsive. The law of gravitation is always attractive. We don't find two masses that, because of their masses, repel one another. If, for some reason, they repel one another, it's because of the application of Coulomb's law, where their charges are the factor that needs to be considered. If one were to take two neutrally charged, two non-charged, essentially, particles, there would be no electromagnetic attraction or repulsion between them.
Oh, no, I didn't want that. I wanted, where did it go? Coulomb's constant. That's what I was looking for. I'm trying to figure out what, it's like, okay, so you know how we have the gravitational constant, right? In the equation for gravity? And I noticed that they're talking about Coulomb's constant right here. I guess that's the little KE thing, the little KE symbol or whatever.
Right.
And so I was wondering what.
A thing like Coulomb's constant or a thing like the gravitational constant can only be determined by taking a measurement where you know all of the other variables in the equation. So, for example, if you have two charged particles and you know what their charges are, so you know Q1 and you know Q2, and you know the distance between those two charges, so you know R, and if you have a way of determining the magnitude of the force that is created, then you know the force, you know Q1 and you know Q2, and you know R squared. And then all you need to do is put those into that equation, and the missing value, Coulomb's constant, is determined by the force you observe and the charges and the distance that you know. So that's the same way that the gravitational constant was determined. Cavendish had two masses that he knew the mass of. He knew the distance between them, and he was able to measure the force that they exerted on one another. And plugging those values into the essentially the equation, he was able to figure out what the gravitational constant was. These constants that exist in the physics of the universe, they're things that we can only determine through experimentation and observation and measurement. There's no way that we could have simply guessed that Coulomb's constant is 9 times 10 to the 9th Newton meters squared over, I guess, Coulomb squared. That's something you can only determine by doing a calculation with values that you know. Just like the only way we know what the gravitational constant is because of an experiment by Cavendish's. That's a value we could never have guessed at.
Yeah, no, I get that. Because as soon as you guess it and then someone else puts it down on paper, it's not going to work.
Right. The things we can guess at, and this might come as a little bit of surprise, the things that we can guess at are the laws of the universe. And what I mean by that is when Newton was coming up with his Principia or Principia, and he was devising these laws of universal gravitation, he wasn't coming up with these out of thin air. He was using the 3 laws of planetary motion that Kepler had come up with before him. Using these 3 laws that Kepler came up with, he was able to say, okay, based on the observations that we know of the movement of the planets around the sun and the movement of the moon around the Earth, it would appear that 2 masses attract each other with a magnitude, with a force that has a magnitude proportional to the product of their masses and inversely proportional to the square of the distance between them. Kepler was only able to come up with his laws based on observations that the other astronomer Tycho Brahe had made over a period of several years, where Tycho Brahe was actually making observations of where do these things appear in the sky. Where, like, he came up with all these points of data, and then Kepler took these points of data and figured out this appears to be a law of this solar system, that if this data is correct, then I can say that the planets are obeying this law. So laws are, in a sense, a guess. They're a way of saying, based on the data I see, this is something that explains the data and can predict the data. Now, that predictability is an important test of a law's truthfulness or whether it really is a law or not. Because before Kepler's laws of planetary motion, one of the things that Kepler's first law was that planets move around the sun not in circles, but in ellipses. Kepler's predecessor thought that the planets moved in circles around the sun. And Kepler realized the data doesn't support that claim. That was why things like epicycles had to be invented, that the planets are making circles around a point as they make circles around the sun. Those epicycles kind of go against Occam's razor. Why should a planet make a circle around a point as it makes a circle around the sun? That same movement can be explained by the planet simply making an ellipse around the sun. So this is all to say that the laws that are devised are the guesses that scientists make. And then they check to see whether future data confirms that law or denies it. And they check to see if their laws can predict future things. This is one reason why Newton's law of universal gravitation, which worked for a pretty decent amount of time, a few hundred years, a couple centuries, they realized that it was not a completely accurate law. It governed some things on the large scale. It governed things, on the scale of Earth, but it didn't explain the movement of Mercury around the sun. Using Newton's law of gravitation, astronomers were able to predict that there would be a planet outside the orbit of Uranus, and that was how they detected Neptune. They tried in the same way to detect a planet between Mercury and the sun, because Newton's law of gravitation said that Mercury should be moving around the sun differently than it is. So obviously there must be something in between the sun and Mercury, an additional mass that's causing Mercury to deviate from the course that Newton's law said it should travel on. And when they realized there is no planet between Mercury and the sun, that opened the door to the Einsteinian theory of relativity, of relativity, relative gravity. That's not the expression. But the Einsteinian notion of gravity explains why Mercury takes the path around the sun that it does. Newton's law of gravity would have required some additional mass of some sort between Mercury and the sun. So laws are the guesses, the educated guesses, that scientists make based on the observations and data that they have. And those laws are refined, and the calculations that support them can be refined. The value that Cavendish got for the universal gravitational constant, he got it to a certain precision, and that value has been refined with better accuracy and with better tools and whatnot. But it doesn't change the fact that, for all intents and purposes, the force of gravity is that gravitational constant times two masses divided by the square of the distance between them. I've been talking for a long time, but I do want to show one more thing. And this has to go back to the question of how do you know what the Earth is made of? So I'd like to share my screen again for a minute here. Okay, so let me make sure it ends up showing up on the YouTube page before I continue. And there it is. Okay. So at the top, we have that the force of gravity is equal to the gravitational constant g times, in the case of the Earth, the mass of the Earth times the mass of the object on Earth divided by the radius of the Earth squared. And what this equation is saying is this is the force of gravity at sea level, because this R is the value between the center of one mass and the center of the other mass. So if we say that that value is the radius of the Earth, we mean that the object is sitting on the surface of the Earth, or essentially the surface of the sea. One thing this law tells us is that the higher up you are from Earth, the gravitational force will be less. And this is, in fact, measurable. You can, if you have decent apparatuses, you can see that the acceleration due to gravity at the top of Mount Everest is slightly less than 9.81 meters per second squared. And you can do experiments even at high altitudes in jet planes, like if you went 10 miles high, about double the height of Everest, you could see again that things fall at slightly slower than 9.81 meters per second squared when you're 10 miles above the Earth. Okay. But so this top equation is the force of gravity at the surface of the Earth. We also know that force in general is mass times acceleration. And so that means that the force of gravity on any object of mass m is the mass of that object times the acceleration due to gravity. We can say that these two expressions for force are identical to one another. They're two different ways of describing the same force. So we can say that g times the mass of the Earth times the mass of some object on the Earth divided by the radius of the Earth squared, force of gravity there, is equal to the mass of the object times the acceleration due to gravity. We have the mass of the object, which is something we can easily know. We have the mass of the object on both sides of this equation. So we're going to cancel them out. And what we're left with is the gravitational constant times the mass of the Earth divided by the radius of the Earth squared gives us the acceleration due to gravity at the surface of the Earth. And we know from actual experimentation and measurements, that's pretty much 9.81 meters per second squared. So using this information, if we know the gravitational constant g, which is something that Cavendish and scientists after him have given us a value for, if we know g, and if we know the radius of the Earth, we can figure out the mass of the Earth. And we do it in this way. So that would mean that the mass of the Earth is equal to g, is equal to the radius of the Earth squared times 9.81 meters per second squared divided by the gravitational constant. So what I've done is I've isolated the mass of the Earth on one side of this equal sign. I've divided both sides by g, and I've multiplied both sides by the radius of the Earth squared. So then you say, how do we know the radius of the Earth? That value can be determined through painstaking measurement. It can also be determined by things such as saying, okay, we know that the pole star is, for all intents and purposes, directly aligned above the North Pole. And so when you're at north 90 degrees latitude, the pole star is 90 degrees above your head. And when you go down to 80 degrees latitude, we see that the pole star is 80 degrees above our head. And if we know the distance between 90 degrees latitude and 80 degrees latitude, then we can determine that in 180 degrees, there's this many miles, and therefore in 360 degrees, there's this many miles. So there are a number of ways of determining or approximating the radius of the Earth. So if you have a value for the radius of the Earth, you have a value for the gravitational constant, and that means you can solve for the mass of the Earth without knowing what the Earth is made of. I mean, it could be made up of 99% helium and then 1% super, 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 super dense elements that we've never even heard of. All that matters is that collectively the mass of the Earth equals some value. And so that's why we don't need to know for sure what the Earth is made of to be able to determine its mass from the law of universal gravitation.
Thanks for the explanation, man.
All right, you're welcome.
I get what you're saying. But like with your equation right there, you still have the acceleration for gravity. So
which I can measure as 9.81 meters per second squared. I can measure that by doing an experiment.
Well, on Earth, right?
On Earth, yes. On Earth at more or less sea level. I'm probably, I don't know, maybe 200 feet above sea level where I am, but 200 feet is a very small fraction of the radius of the Earth. Actually, let me show you how your distance from the center of the Earth affects this equation. I'm going to use, okay, let's see. Mass of the Earth. Okay, so 5.972 times, times 10 to the kilograms. G times that divided by, what is it, like 6,378 kilometers squared? Radius of the Earth, 6,378.
But isn't there a variable that we have to keep in mind when we do experiments on Earth and then trying to relate that to orbital bodies?
And what would that variable be?
The atmosphere.
Okay, hang on. Brain grunt. Yes, we can know some things about the inside of the Earth, but we don't need to know those things in order to figure out the mass of the Earth based on the gravitational equation. That was the point I was trying to make. Back to your point.
Yeah, and you crushed it with that one, just to let you know. Like, that was actually a very good explanation, man. I mean, I'm so... It's not that I'm not buying it. It's just that I get what you're saying, but at the same time, like, to me, it's almost like comparing apples and oranges. Like, an experiment here on Earth, and then what they tell us about space, which is supposed to be a voidless vacuum, or a voidless. That was fucking stupid. A vacuum, right? No particles, no crap. As soon as something starts floating at 1,000 miles an hour, it'll keep going 1,000 miles an hour until something slows it down, kind of deal, right?
Right.
But we don't have that here on Earth because we got an atmosphere. As a matter of fact, did you hear about the meteor that flew and crashed into South Africa?
No, I hadn't heard about that.
It's been over the last couple of days.
No, I haven't seen it.
I was talking with someone about this because we're told that these things are traveling, and this is just an estimate, like 30,000 miles an hour or so, right? As they're entering into the atmosphere. Well, if it's traveling 30,000 miles an hour, how fast would it be traveling, or how quickly would it get across an area of like 50 miles, right? Mm-hmm. Wouldn't it be like in a split second, like literally like a blink of an eye, and you'd miss it?
Well, yeah, you can simply do the math. If you have an idea of the speed of the meteor and you know the distance between the surface of the Earth and the edge of our atmosphere, then you can say, okay, it should take about this long to go from the edge of our atmosphere to the surface of the Earth. However, the atmosphere is increasingly thick or increasingly dense as you get closer to the surface of the Earth. When the meteor is traveling through the vacuum of space, there is no medium to slow it down. As soon as it hits our atmosphere, it begins to slow down. Some of the energy it's using for its speed becomes heat energy, which is why we see when meteors are entering the atmosphere, that's why they illuminate, and that's why they leave this trail. Because, and it's the same reason, for example, that things like the space shuttle, when it enters the Earth's atmosphere again, it has to have that heat shielding on it, because it's going very quickly into a thickening medium. So it generates heat and slows down.
And that slows it down, right? The atmosphere slows it down?
Correct.
So that's kind of my point with doing experiments on Earth and then trying to relate those to the vacuum of space with the orbital bodies. How is the gravitational constant what it is on Earth and the same out there when we have things working against us here on Earth and nothing's working against them out there?
Okay, I will get into that in about 2 minutes.
Oh, no, dude.
The first thing
I just throwing it out there while I still had it in my head, bro.
Yeah, and I will address it. So the first thing I want to do is show how your distance from the surface of the Earth affects the acceleration due to gravity. So for some reason, I really can't explain this at this very moment, and I wonder if somebody in the side chat can. So when you're using Google, Google knows a lot of like the physical constants and mathematical constants. So like I can type up here pi times 5, and it'll give me, you know, that value there, which represents 3.141592654 times 5. I don't need to write the digits of pi out. It knows what pi is. So you can do things with g times, you know, a number, g times 1. Okay, so that gives me what the gravitational constant is. So I have written here g times, and then a value for the mass of the Earth. And then I have that divided by the radius of the Earth in kilometers squared. And for the life of me, I don't know why the value it's giving me right now is 9.798 meters per second squared. I expected it would show me 9.81 something meters per second squared. Maybe I've been using, I don't know, maybe we have a better value for the radius of the Earth in the last hour or two. I don't know. But my point is, let's treat this value, 9.798 meters per second squared. That is the acceleration due to gravity at the surface of the Earth at 6,378 meters, kilometers from the center of the Earth. Okay? If we go up into the atmosphere 1 kilometer, the force of gravity, the acceleration due to gravity barely changes. You see the value goes from 9.798 to 9.795. That's a very small change.
Now, but isn't that kind of making an assumption that you know that you're already on a ball and calculating it from the center of the ball out?
Yes, that's what Newton's law of gravitation says.
Okay, gotcha.
Yeah, I mean, that's what he's saying. You know, two spheres, however dissimilar they are, you know. So this is all assuming we live on a sphere. Okay.
Yeah.
So that's the acceleration due to gravity at sea level. That's the acceleration due to gravity at 1 kilometer above the surface. That's 10 kilometers above the surface. It's 100 kilometers above the surface. So you can see that the value of acceleration due to gravity is changing the higher up from the surface of the Earth you are. And you would probably, if you were 100 kilometers up, you would probably be able to conduct an experiment with, you know, decent equipment that would show you, wow, things really are accelerating with a smaller, things really have a lower rate of acceleration when we're 100 kilometers up versus when we're 1 kilometer up. So that just goes to show you, like, how far away do you really need to be from the surface of the Earth before the Earth's gravity has a essentially negligible effect? Look at this. We're 10,000 kilometers now above the surface of the Earth, and there's still an acceleration due to Earth's gravity of 1.48. Okay? The further we go away from Earth, the less we feel its gravitational pull. Okay? So that was what I wanted to show about how your distance from the center of the Earth, or your distance from the surface of the Earth, that affects the acceleration due to gravity that you experience. So now moving on to your question about how do we know that things in space are operating along the same principles as things here on Earth? And it is a perfectly valid point. And the answer to the question is, first of all, yes, so Newton has these laws of motion. And one of them is that an object in motion tends to stay in motion, and that an object at rest tends to stay at rest until a force is enacted upon that object. Now, as far as we know, in the vacuum of space, there is, you know, if you're hovering in space somewhere, okay, and you throw a baseball, there is nothing in space to stop that baseball from moving in the direction you throw it with the speed that you've thrown it. Actually, let me take that back. Gravitational forces will begin to pull that object maybe off of the trajectory. But if we assume that there's absolutely nothing out there in space except you and the ball, when you throw that ball, it will continue to move in that path at that speed because there's no other force acting upon it. On Earth, there are plenty of other forces that can act upon things. And you bring up air resistance or atmosphere as one of those things. I know that if I were to drop this beer bottle from my desk to the floor, I know that air resistance on it would be negligible. I know this because of the dimensions, the mass. I know this because of the makeup of the bottle. It's a completely different question of what if I drop this beer coaster off of my desk? It goes a whole lot slower. Well, it goes a whole lot slower if I drop it flat. And the reason it goes slower is because now air resistance comes into the equation. Air resistance doesn't come into the equation with my beer bottle simply because of its shape and its mass and the other factors. My coaster here is cardboard. It's kind of stiff cardboard. And if I drop it flat, it takes longer to hit the floor because there's more air resistance involved. If I drop it edge first rather than flat, well, it twists around a bit. So the gravitational constant G doesn't care about air resistance. It doesn't care about atmosphere. What we need to do in those cases is write a more complex equation. When you're taking physics classes in high school, you're always being told, assume a frictionless plane or assume a frictionless ramp and assume there's no drag on the thing you're dropping. And that's how you do those equations so that you don't need to say, all right, so this is the acceleration due to gravity. This is the deceleration due to air resistance. This is the deceleration due to friction. And this is the acceleration due to the fact that you accidentally pushed the object. You didn't just release the object, okay? So the way, I guess the way that we go from here is we say things on Earth, assuming atmospheric drag doesn't come into effect, will drop at 9.81 meters per second squared. We know this doesn't happen when there is air involved because you can see that when you drop a hammer and a feather, the feather takes a much longer time to float down and hit the ground. They have done experiments in vacuum chambers, a very, very large vacuum chamber, dropping, I believe, a cannonball and a feather in, I think it was like a 3-story vacuum chamber. There's a video of it on YouTube. They remove all of the air from this chamber so that there is no air resistance. There's essentially no atmosphere. And sure enough, the feather drops as fast as the bowling ball. Now, this doesn't mean that if you were standing beneath them and you had your hand out and the feather fell 3 stories into your hand, it doesn't mean your hand would break because the mass of the feather hasn't changed. The speed it falls with is the same speed, or the acceleration it's fallen with and the speed it's fallen with is the same as the acceleration and the speed of the bowling ball because there's no air resistance to slow down the feather. But the mass of the feather is still so much less than the mass of the bowling ball. It's because we can do experiments in vacuum chambers like that that we know that this gravitational force doesn't depend on the mass of the object itself. So if we can recreate on a small scale a vacuum on Earth to do these experiments in, and if we have a reasonable certitude that space itself is essentially a vacuum, and I would say that we can know that because we've sent rockets up there and we've sent people up there and we've done all this stuff up there. But the movement of the celestial bodies corresponds to movement through a vacuum. We don't see signs of them moving through atmosphere. We don't see signs of them having friction or drag interfering with their movement. So that's how I would address that. That it's not simply that the value for G, the gravitational constant value, capital G, it's not one value on Earth and a different value on the moon and a different value in space in between. No. Big G is a universal gravitational constant that deals simply and only with the gravitational force between two objects. It doesn't care about and it doesn't deal with air drag or friction or tension due to one of the objects being on a spring or a cord or a wire. G simply deals with the force of attraction between masses.
You just brought up that we know that space is a vacuum. I asked myself this question a few weeks ago, actually, a couple weeks after our last chat, as a matter of fact. Because, dude, growing up, I was always the kid that was asking why, you know? Like, when my grandpa would tell me that I need to get this many hours of sleep, I need to eat these foods for breakfast and these foods for lunch and these foods for dinner, I was the kid that was going, well, who the hell says? Like, who says, you know what I mean? Like, why? Well, I asked myself the question, who said it was a vacuum? And dude, I love chatting with you because of just the way you approach things. Can you think, in all the crap that you've learned, did you ever learn who said it was a vacuum?
I know that at first it was not believed to be a vacuum, that they believed that there must be some ether, you know, some medium out there in the universe. And I know that there were a number of experiments done in the late 19th century and the early 20th century that were attempting to prove the existence of ether, to prove that there was some medium that existed out there in the universe. And one reason that scientists, not philosophers, but scientists believed that there had to be some ether, there had to be some medium there, is because they believed that light needed a medium through which to propagate. Sound waves need a medium through which to propagate, which is why they say in space, no one can hear you scream. Sound waves cannot travel through a vacuum because sound waves need to vibrate a medium in order to transmit themselves. And it was believed that light also needed some medium through which to travel. That the experiments that were done that attempted to prove the existence of the ether failed to show the ether's existence. And you've probably heard of some of them, like the Michelson-Morley experiment and whatnot. Right, so I don't think it's so much that some scientists said, oh, space must be a vacuum. It was simply, oh, space isn't filled with ether. And I think it was probably the fallout from space not being filled with ether.
Actually, it's funny that you were talking about science versus philosophy, because the idea of a vacuum, it's, believe it or not, it's backwards from what you just explained right now. It wasn't the scientists that said, it was the philosophers actually in like 450 BC. And it actually has to do with the nature of the Greek god Cosmos. Is where that's coming from. Let's see, who was the guys that did this? Most Epicurus. I'm pretty sure you've heard that name before, right? I probably butchered it right now, but yeah, he ancient Greek philosopher who founded a school of philosophy now called Epicureanism. Only a few fragments and letters of Epicurus' 300. Yeah, this guy was one of the guys that. So I understand that they say it's a vacuum because they say they launched a rocket up there, went to the moon, and it was a vacuum. But that kind of goes back to the whole idea of what experiments were done. Because I was looking for this the other day. What experiments were done that told us that space was a vacuum? Besides them telling us they launched something up there and said, oh, yeah, it's a vacuum.
Okay. One way that we can determine it is the existence of air pressure. Air pressure at sea level is one value.
But air pressure, get into that kind of can also prove that we're in a container at the same time. If you want to go air pressure, like if we're throwing out everything we know and starting from scratch right now, and we're both looking up, and you're telling me that because of the air pressure, the way that it's heavier down here and gets lighter as you go up, that it's eventually going to get into a vacuum, and I go, well, no, and I show you some fog in a bottle, and it's settling at the bottom and slowly dissipating as it gets to the top, I'm showing you the same thing that you're telling me. And wait, but kind of have to be a wash, right?
I haven't heard this line of reasoning. It doesn't prove that there's a lid, though. I suppose there could be a lid.
I know. But I'm just saying, if we were both on the ground and we're starting from scratch, you would be postulating that there's a vacuum because of the air pressure, right? And if I show you an example of a jar where the pressure is because of the stuff in the jar, everything's thicker at the bottom than it is at the top, that'd basically be like the same thing.
But that would be true even if you didn't have a lid on the bottle.
True. Very true. Yes.
So it doesn't prove that there must be a lid.
In all actuality, we just proved that it could be three different ways. Like it could have a top, it could not have a top, or it could be less pressure and then leaking into a vacuum. Or wait, that's wrong. I'm putting words in your mouth doing that.
Right.
Less pressure, and then there's a invisible wall, and then a vacuum.
It's not that there's an invisible wall. It's simply that there's a point where the pressure is a tenth of what it is at sea level, and there's an area where it's 100th of what it is at sea level, and an area where it's 1,000th of what it is at sea level, so on and so on until it is essentially zero pressure. And as Beach 8 is saying in chat now, the lid on the Earth's atmosphere is gravity. There comes a point where the particles of gas are so far away from the surface of the Earth that Earth's gravity no longer attracts them to Earth. That is what stops the Earth's atmosphere from expanding forever. The fact that the gravitational force.
Hold on. Sorry. Run that by me again.
Okay.
So once it gets to a certain point, gravity.
Okay.
Gravity.
The gravitational force on Earth pulls everything. Okay. Yeah. Even molecules of gas. Okay. But as I've shown before, the further you get from the surface of the Earth, the less acceleration due to gravity there is. Okay? So there comes a point where particles of gas are not attracted to the Earth fast enough or strongly enough that they are part of the Earth's atmosphere. I don't know. Brain Grunt is telling me I have this wrong.
Oh no, I think he was just saying that the first time you said it, it came. I think it came out a little backwards. That's why I was like, wait, what? Because it sounded like you were saying that at the edge of the atmosphere is when gravity's less on whatever particles are up there, right? Whatever gases are up there. But that, when I think of that, it makes me think of which is stronger, gravity or a vacuum. And I think I asked you this before, actually.
Right. But a vacuum, if a vacuum is what we believe a vacuum is, a vacuum has no strength. A vacuum has no power of its own. Things like vacuum cleaners on Earth, there's suction involved there through motors whirring fans and creating suction power and all that. A vacuum in and of itself is simply an empty space. I would go as far as to say Earth's not a perfect vacuum because there's particles meandering through there somewhere. There are bound to be gas particles floating through space, but they're just not part of our atmosphere. So maybe the vacuum of space is 0.000000001 psi. Yeah, I guess it comes down to, like, you know, if the force of gravity is real, then that would be a reason why we don't need a dome over the Earth in order to stop air from leaving, because it's not that the vacuum of space is sucking it out. And you know what? You could even say the vacuum of space is trying to suck the air out. The problem is that the force of gravity is strong enough to a certain extent on Earth to keep some of that gas from going into the vacuum. But it's a gradient, which is why as you get higher and higher up, the air is getting thinner and thinner. The density of the air is getting thinner and thinner. And eventually you get to a point where it's perfectly thin. There's nothing there. So yeah, that's how I would explain it.
Well, here's an example of a vacuum beating out gravity. When you take a glass, fill it up with water, and this is what we talked about before, right? The last time?
Right. There's additional forces at play here. There's not simply gravity and vacuum.
gravity should be pulling the water down, and the
gravity does pull the water down. You can see the gravity is pulling the water down because the water is at the bottom of the glass here. Gravity is also pulling the coaster, or I don't know, index card or CD case. I don't know what that is. Gravity is also pulling that down. But in this case, the force of, the tension the seal made, and yes, also the force of the vacuum up at the top of that glass, that is keeping the thing glued up to the glass. I would hazard a guess that the vacuum in operation in this experiment here is a stronger vacuum. Or no, that's not the way to put it. How to describe this? The forces at work in this experiment are strong enough to overcome the force of gravity on the water and the piece of cardboard or whatever it is. Because yes, gravity wants to pull that water all the way down, as far down as it can go. But the vacuum at the top of the glass. But just because this experiment has essentially a dome at the top of this glass, that doesn't prove the Earth needs to have a dome.
No, I'm not saying that. I'm just saying I'm still wrapping my mind around the vacuum versus gravity issue, because okay, so astronauts, pilots, a lot of these guys, they train in vacuums every now and then, right? We have experiments that we're able to see inside vacuums. Anytime you put something inside a vacuum, I like watching Action Lab. Action Lab's a fun channel to watch. He likes putting anything in a vacuum. It's pretty cool. He put his arm in a vacuum, actually. I'm afraid the guy's gonna die in the name of science one day.
He wouldn't be the first.
But anytime he puts like a liquid in a vacuum, it boils.
Yeah.
Or it actually, what's really cool is that there's a time where it will boil until it actually freezes. That's pretty badass. So, but like you were saying, that vacuum that he would be using for that experiment wouldn't be a good example of the vacuum that they experience in space, right? We're kind of talking about apples and oranges here.
Yeah, I'm not sure how to apply one situation to the other. I'm not sure how to compare.
And that brings me back to, where can we see this? We're told that this vacuum up there is like this. It's this empty void. And we have no way of even duplicating that, though. Like, our best way is a vacuum chamber. And then we're told that that vacuum chamber isn't anywhere close to what's actually out there. And then I find it funny that the astronauts actually train more in water than they do in a vacuum, which is kind of the opposite in reverse, right? Water's pressure.
It's way easier to train in water than in a vacuum. And I'm pretty sure they train in water so that they can simulate the effects of lower gravity rather than so that they can simulate the effects of a vacuum. It's way easier to have a pool full of water than to continually create a vacuum chamber, because that vacuum chamber loses its vacuumness every time you open the door. Like,
yeah, you can't be walking in and out. I get that.
right.
And you know what? Right now, I said that we know that they do the test in a vacuum. It's actually really hard for them to find where they run a human test with somebody in a spacesuit in a vacuum. You'd be surprised. They're not.
Yeah, I don't know where they do that.
Well, you would think that they would have a video for every time a new astronaut showed up, right? Like, wouldn't that kind of be like their rite of passage is sitting in the vacuum chamber with the freaking astronaut suit on? As they're training?
I can't guess at what they do.
Oh yeah.
I would also say that our desire for, or our fascination with, video evidence of everything that happens is more a modern thing, because nowadays there are video cameras everywhere. I don't think it's reasonable, though, to assume that everything that happens at NASA is being videotaped. I would assume that certain experiments are videotaped, and I would probably imagine that things where human life is on the line are videotaped, because if something goes terribly wrong, they need video evidence. But I don't honestly know how many astronauts do tests in vacuum chambers on Earth, and I have no idea if any of them are videotaped while doing so. What I do know is that the rockets that SpaceX launches, they have video cameras on them. And I agree with you. It would be awesome if we could get a single uninterrupted video feed from launch to landing from a single camera constantly streaming. That would be amazing. I would love it because it would be cool to watch from start to finish. And I would also love it because it would put to rest a lot of the conspiracy theories and doubts about the possibility of space travel and the possibility of going up into the upper reaches of the atmosphere and out of the atmosphere. I think Beach 8 is saying that they do have a single shot. Beach 8, is there a SpaceX video that is a single camera from launch to landing, continually running, publicly available? Every launch I see, and I'm not trying to take the role of the conspiracy theorist here, but every launch I see, they are always cutting from one camera to another. They once the craft is out in the upper reaches of the atmosphere, they're always showing you, this is what the exhaust nozzle looks like from the left for 10 seconds. Now this is what the exhaust nozzle looks from the right for 10 seconds, and then back and forth. I would be interested in seeing a single camera for all the 30 minutes of the launch.
Yeah, so dude, you are not the only one. So speaking of launches though, real quick, I was asking you about the Russian one today, right?
Mm-hmm.
And I was watching it, and it cut out prematurely because I think they had a glitch. And it's kind of weird because right here we have the view that like SpaceX usually has, right? Where you see the Earth down here, you see the butt end of the rocket with the camera pointing down, right? Typical view that we usually have.
Mm-hmm.
And then all of a sudden the Earth starts scratching like it's on a turntable. And at first I thought it was the whole feed doing it. And then I went back and slowed it down to see if I could see the rocket moving as well. Because if it was the whole feed, everything in here would be moving, right? Like jumbo, like let's say it hit some kind of turbulence or whatever. I have no idea what would cause a freaking camera on the side of a rocket to move. But this was interesting because like the Earth, it looks like someone put it on a turntable and was scratching it, like, and it's hilarious because it's actually right when the woman doing the interview with the astronaut, she goes, and that means they're in space, right? And right as she gets that out of her mouth, you see the Earth go tick, tick, tick. Like, here, watch. Just it takes like 10 seconds, dude. So the Earth is going nice and smooth, and then watch, it'll. And then the feed cuts out.
Okay, that looks like we got about 3/4 of a second looped over and over and over again.
No, actually, this is
No, when you say it looks like it's scratching like a record, it looks to me like at the end of that feed, it suddenly started looping the last 3/4 of a second. That's
but
that's what it looks like to me.
But it's only the Earth that's looping like that. The rocket.
The rocket. Why would you expect the rocket to move? The camera is mounted on the rocket.
Okay, so if it was looping, right, like you said, then wouldn't the gap, right? Because like what I'm looking at right now is the gap between the Earth and the edge of this rocket right here, right? So you were saying that the footage looped real quick, right?
Yeah, it looks like when it starts to skip like that, we're getting about 3/4 of a second suddenly replayed over and over and over again. Because the motion of the Earth, every time it repeats like that, it's the same motion of the Earth that we saw right before the skipping happened. Like if you were to do a frame by frame analysis, I suspect you would see that we're seeing the same, I don't know, 12 frames looped over and over again. It would be more apparent if in that moment of time there was some like change of lighting on the rocket. We would expect to see that effect also be looped. But because the camera is part of the rocket itself is never moving in the frame at all. Like you could put your mouse on that little white node of the rocket, which is like to the left and just a little bit down. If you played like the 10 seconds of the video, I don't think that little white node would ever move because the camera is mounted to the rocket. It's actually one of the most like disorienting features of selfie videos when like the camera is like body mounted to somebody and you see everything around the person moving and their head stays like perfectly centered in frame. It's the most disorienting thing because that's not how we perceive things in reality. But it's because the camera is mounted to the thing.
Well, yeah, and you know what? Thanks for the advice on actually going through and looking at it frame by frame, because that's what I'll probably be doing with this next one. Yeah, and that's why, dude. That's why I like talking to you guys, because whether I agree or not, it at least stimulates different thoughts. It helps, I don't know, move things along. But yeah, that was the rocket launch earlier. But okay, so if that was just a loop, right?
Mm-hmm.
where okay, so it's a live loop.
It looks like they lost the video transmission because it goes to suddenly a green screen, which is like the worst thing I could ever possibly say here. But yeah, they lose the video feed, and I honestly don't know how any of their technology works, but the video stopped being transmitted and it looped the last, like I said, 3/4 of a second or so over and over and over again. I don't know why. That just appears to be what happened. And I don't claim to know why that happens. It's just simply that's what it looks like to me.
Yeah, no, and that's why I'm throwing this out to anybody, dude. I don't care if you're a flat earther. I don't care if you think that we live on a ball. I don't care if you think that we live on a fucking spinning pear, dude. It really doesn't matter. You have your opinion on what you saw, and I guess you know what? Even though we disagree on pretty much just about everything, at least we're able to bounce ideas off each other, man. Like me and you tonight going through like Newton's law of gravity and stuff like that. I can guarantee that there's a lot of people out here that think we live on a globe and that think that the earth is flat, and they don't know this shit about gravity that we're talking about right now. I'm not saying that they don't know anything, but I'm just saying it's just looking at things differently. Like I was saying, dude, when I look at Newton's equation of gravity, that it looks like he copied freaking Coulomb's, dude. Like it almost exactly. It's weird. It blows me away. But thanks actually for going over that one with me. I kind of want to dig into Coulomb a little bit more in my travels later on, because personally, I think there's some kind of connection right there with Coulomb and Newton. I think the idea that both equations run off of an inverse square.
Well, that's because they deal with a force between two objects. Now, Coulomb's law is like a century later than Newton. So, and again, Newton didn't formulate his equation as F equals a constant times two masses over the radius squared. He simply said the force is proportional to the product of the masses, and it's inversely proportional to the square of the distance between. Because again, he didn't know that constant value. I don't know the history of how Coulomb developed his law, so I don't know if in Coulomb's Principia or whatever it is Coulomb wrote, I don't know if he writes it as explicitly as we have come to know the equation. But yeah, Wikipedia admits, being an inverse square law, it is analogous to Isaac Newton's inverse square law of universal gravitation. But again, that's because it seems rational, and apparently it is experimentally proven that forces between objects tend to relate to the square of the distance between them. I mean, we use inverse square laws for things like brightness, because if you're shining a flashlight at a wall, and let's say it takes up 1 unit of the wall when you're 1 meter away, if you move 2 meters away, the light will take up 4 units of space on the wall. That's the square of the distance from the light source to the wall. It's just kind of one of the ramifications of the universe we live in. And I believe, like, technically the reason is it has to do with the fact that the area of a sphere is related to the square of its radius. And that's why this inverse square ends up happening.
Well, and Jeff, can I just say thank you very much for your answer on the whole wanting to know what the barrel weighs from across the yard? Because that was probably the best answer I've gotten over the last like 3 weeks. Everybody else keeps throwing like mass spectroscopy at me and stuff like that. And
well, yeah, somebody in chat said that, you know, using the right high-end equipment, you can do all this analysis on the barrel from where you're standing. But that kind of answer to your question isn't really getting at the meat of why you're asking it, which is like, how can we know the mass of the moon and the earth before we have all these mass spectrometry and, you know, all this high-end equipment?
Okay, so I accepted the whole idea of the mass spectroscopy. All right. And I was like, okay, so let's go with that. Let's say that we're able to tell what something is by the light that it gives off, right? And so when you break down the rainbow, though, there's what, 7 colors in the rainbow, right? And so that means that we have like 7 options to be able to tell what something's burning, like green, yellow, blue, red, orange, all right, indigo. We only have so many options.
Well, see, that's a simplification. Those colors that we've named they correspond to certain wavelengths or certain bands of wavelengths of visible light. And light is made up of so much more spectrum than simply the visible light. And when you do something like mass spectroscopy, you're not saying, oh, okay, this shined back blue, green, and red. You're saying, okay, light is coming back at these wavelengths, and at these wavelengths, and at these wavelengths. And while it's usually presented to the public as bands of color, there's actually raw numerical data behind that. You know, red light that we perceive as red corresponds to a certain range of wavelengths of light, and light that we see as green corresponds to certain wavelengths. And mass spectroscopy is determining what those ranges of wavelengths are and then rendering them in colors that we can understand as a guide. But really, the numerical values of the wavelengths, rather than how they're rendered as a color, those are the most important things. But yeah, like mass spectroscopy, which I did a couple times in high school with really fancy equipment, and it was cool. That's not really a practical way to help somebody understand things like gravity.
Yeah, I was going around and around and around with them for forever on that. But your answer that you gave, right, is much better and explains things a lot. I'm able to understand where you're coming with that, you know? Like I get that one. Looking at a light and someone telling me how much that light weighs. No. But what you said, as far as being able to calculate it by going around and not needing to know the mass, I can see that. That's a different way to think about it.
Right. Yeah. And it comes down to like the fact that these formulas allow us to cancel things out, like the mass of the other object, we can cancel that out even though we know it. Yeah, it brings us down to we either have to know the radius of the Earth or we have to know the mass of the Earth. And the radius of the Earth is a lot easier to figure out.
Well, and that's only calculating with like Earth and the moon or Earth and the sun or okay. But what about what about when you're looking out at like Jupiter, right? Because back to the whole issue of just looking at something, if I have an object and I'm half a mile down the street, right? Let's say that I have a 3-foot pole in my hands, right? Or a 3-foot piece of like 2x4. All right. From half a mile away, can you tell whether that's 3 feet or 5 feet or a foot?
Sorry, could you repeat this?
I'm basically just trying to say how hard it is to judge things when they're at a distance. Like if I was half a mile down the street from you and I had something in my hands, right? Let's say it's a 2x4 and you had no idea how tall I was. Okay.
Right.
You had
okay, yeah.
you weren't able to relate that at all. Could you tell whether the 2x4 I had in my hands was 3 feet, 5 feet, 6 feet, a foot?
No, the best I could do is I could know its angular size. I could know how much angle it takes up in my visual space. But I would need to know either the distance from me to you, or I would need to have another known length that I could put in the area of you and the 2x4.
And that's the other problem I have with trying to figure out. Because, okay, so when I ran into asking people, how can you tell the mass of something just by looking at it? And they kept throwing out, someone said mass spectrum, tongue twister. It wasn't spectroscopy. It was a spectrometer. It was where they break down the chemical, like what's in something, you know, and tell you what it's made of. That was the first thing that I heard. And I was like, well, but you can't touch the object that I'm talking about. Like, and so then they went into light mass spectroscopy. And then when I looked that up, that assumes that you know the distance of the object and the size of the object that you're looking at to be able to calculate it using light spectroscopy. Well, like you just said right now, with knowing how big of a 2x4 I have in my hands, you would have to know how far it is from me to you and have something to relate that to.
Right. Another way I could do it is with 2 observers rather than just me as the observer. And essentially, if I know how far it is from me to the other observer, we don't need to know how far it is to you. We just need to take, we essentially compute parallax on the 2x4 that you're holding. And if we know how far we are apart from one another, me and the other observer, not you, then we can use that to determine the size of the 2x4. That's one way that people on Earth can approximate the actual size of the moon. And it's an experiment I love because it really is something that takes very little resources. Like, it doesn't require fancy equipment, and it requires like high school trigonometry at best. And it simply is, two observers who know how far apart they are, taking simultaneous observations of the moon. And they can compare their two observations, know how far apart they are from one another, and use that to get the distance from them to the moon. And then they can use the angular size of the moon to approximate the size of the moon. So it's not an experiment for us to do tonight because it's getting close to my bedtime here. But it's definitely something that we could try another time.
Yeah, dude. I am more than willing to hop on here and chat with you again, man. It's been fun these last 2 times.
There's one more thing I want to do. One little experiment I want to close with. And it's not necessarily something, and I'm sorry we didn't get to talk about Project Echo. I can read up more about it so that I can talk intelligently about it next time, though. But the thing I wanted to bring up, and I don't know if this is something you personally, as a flat earther, ascribe to, or as an alt-earther, I don't know what term you would prefer to use for yourself.
Dude, you can call me a flat earther, man. It won't offend me or anything like that. I don't know what else to call myself anyway. Okay.
You've probably seen videos that talk about, if you're on the shore of the beach at sea level, you can see boats in the distance, right? And things like, as the boat gets further and further away from you, it becomes too small for you to see. And so you then take a camera with a zoom lens, and if you zoom in, you can see the boat again, right?
Mm-hmm.
Okay. Now, the Globers say that eventually, or these videos produced by flat earthers say that when you can't see the ship with your naked eye, it's supposedly gone over the curve. Now, that's not what globe earthers say. Globe earthers say when you can't see it with your naked eye, it could simply mean that it's too far away for you to detect it because its angular size is so small. And things like binoculars or zoom lenses on cameras or telescopes, they increase the angular size of something so that you can see it. So the flat earth videos that I've seen, they say that eventually it's true that the boat will go so far away that you really can't see it anymore, not even with binoculars and not even with a P900. And the reason you can't see it is because it's simply too far away and you're looking through too much atmosphere and you just can't see the boat anymore. Have you heard that argument and have you seen videos that make that claim?
Yeah, I have.
Okay. Now, are you also aware that on Earth, regardless of whether the Earth is flat or a sphere, on Earth, when you see something appear to go over the horizon, if you increase your elevation, if you go higher up, you can see it again?
Yeah.
Okay.
I get that.
Now, here is why I think that fact alone ruins the credibility of this particular flat Earth argument. And I'd like to show you why in this little GeoGebra demonstration here, okay? I have over here on the left, Observer 1, okay? Observer 1 is standing on the shore of a beach, and 1,500 units away from him is a boat. And we're going to say that 1,500 units away from him, the boat has now disappeared from his sight. He can't see it with his naked eye. He can't see it with a P900. He can't see it with a telescope. And
Gotcha.
according to Flat Earth, it's because of perspective. It's because at this point, it's just too far away. It's too small, or there's just too much atmosphere between you and the boat. Okay?
Okay.
Now I would like to introduce Observer 2. Observer 2 goes up in elevation. He doesn't get he doesn't change his location on Earth. He simply goes up 300 units. Maybe he uses a drone or something. I don't know. Or he climbs a ladder.
Or like,
He's
let's
now,
say that's like, this is like your vertical line right there is like a building, and he's on the roof and the guy's on the ground right now.
exactly. Okay. So observer 2 is higher up than observer 1. And from observer 2's location, now he can see the boat again. Okay. This is something that can be demonstrated in real life. Okay. And by the way, in chat there, Charlie, that is exactly, okay, that's not exactly the experiment I have in mind, but that is a very similar experiment. And thank you for mentioning it. Okay, so back to this little model here, and then I'm going to go to bed. Observer 2 can see the boat. The problem with this as a flat Earth argument comes in when I show you the triangle that we've created. Okay? Observer 1 is 1,500 units from the boat. And apparently, according to the flat Earth argument, at 1,500 units away, the boat is either too small or you're looking through too much air to see the boat. Observer 2 has gone up 300 units, and from where he is, he can see the boat. The problem is that observer 2 is more than 1,500 units away from the boat.
Yeah,
observer 2 is looking farther than observer 1, and he's looking through more air than observer 1, and yet he can see the boat. This, I think, is a big problem for this particular flat Earth argument.
Yeah, and I see where I totally see what you're bringing up there and where you're going with that. And okay, so I've been thinking about this for a little while now, when the boats disappear and when they come back, right? Because everyone always asks, why do they disappear bottom first, right?
Mm-hmm.
And why do they come back top first when they come back into view? Especially on the water, I think it's not so much just the atmosphere, right? Because, I mean, atmosphere kind of seems like a cop-out sometimes, especially when you're dealing with water. When you're dealing with water, we have to take into account, like, especially if the sun's out, evaporation, right? When things evaporate, that's basically the water being distilled, and it's rising. So I think that the closer to the water, you have more distortion. That's why I think with observer 2, when you get up to the 300 feet or the 300 mark, now you're above that, and even though it is farther, you have a much clearer view because it's kind of a line of sight thing. You're not having to look through right above the water. And that's one of the problems. So, okay, I'll give you an example, dude. This weekend, there's a meetup out here in California. And they're going to be doing I think a laser experiment or a visual experiment on the Salton Sea here in California. Personally, I think they're gonna boggle it. They're gonna screw it up. It's not any flat earthers that are actually doing it. It's skeptics that are doing it. And I think they're gonna run into the same issue that all of us have when we're trying to film things on the water. And I saw you lowered it down to 200 right now. Now, if you do lower it down to 200, would their view, or not 200, 100, would their view at 100, I imagine they would be able to see the boat clearer than at ground level, right?
It really doesn't matter how much higher you move it. What we know from experimentation on Earth is, as soon as something has apparently gone over the horizon, you just need to increase in elevation a little bit. Like, you don't need to increase your elevation 3 times or 2 times. Just going up a little bit in elevation brings the object back into view, which is why there's a bunch of YouTube videos of drones hovering at like ground level. They see the sunset, and then they go up a foot or two, and then they see the sunset again, and then they go up another foot or two, and they see the sunset again, over and over and over. So,
well, I mean, I can do the same thing if I watch something go out of my view while I'm laying down on the ground, and then I stand up, I see it again.
Exactly. And so you've only gained about like 5 feet of elevation. So how different is the air you're looking through? Especially considering that the angle of you to the object, if the object is, for example, 3 miles away, and you increase your elevation by 5 feet, a triangle with an altitude of 5 feet and a base of 3 meters, a base of 3 miles, I can tell you what that angle is. Arc 10 of 3 miles over 5 feet in degrees. 5 feet over 3 miles. 0.018 degrees. So that 0.018 degrees is the angle change of all that air that you're looking through. You're not looking through like a 45-degree angle difference of air. You're looking through, for all intents and purposes, the same air. And you're looking through slightly more of it.
So then, Jeff, I got a question, because another thing that I hear from a lot of people is that the Earth is just bigger than you think it is, right? To me, that doesn't make any sense personally, because I just, in my head, like, okay, so just on average, the Earth is what, close to around 25,000 miles around, right? 24 and some change.
Yeah, 24,901 is the value that I have stuck in my head.
Okay, so like 25,000 miles is 25,000 miles, right? So how far, just so I can have an idea, from somebody who's not a flat earther, how far would something have to go for you to legitimately say that it's behind the quote curve? And let's just say it's an object 10 feet tall, to make it simple, man. I don't want to be getting into like 300-foot ships and stuff like that.
Yeah.
And it's got to go like 800 miles out before the 300 feet disappear. No, I just make it simple, like 10 feet. Like an object like 10 feet, about how far do you, like how many miles do you think it would be going before it dipped below where you could see it?
Okay. If I'm 6 feet tall, okay, or my eyes are probably, well, I'm 6 feet tall. My eyes are a couple inches below. Let's say my eyes are at the 6 foot level. And let's say I'm standing exactly on the surface of the Earth, and it's completely smooth in every direction. Okay, we're talking about an ideal Earth with no bumps or anything. 24,901 miles in circumference. Okay. At about 3.1 miles, the bottom of the object would disappear. And so just a little further past that, the whole 10-foot object would no longer be visible. It's the sort of thing that I can mock up in GeoGebra in just a couple minutes. If you'd like to see, the actual value.
Oh well, dude, hey, bro, we can go over this next time, man. I know
Okay.
that you're getting ready for bed and all, dude. I was just, yeah, you know what? Keep that in mind for next time, and
Yeah.
I'll mull it over as well, and I'll keep asking people and see what they say, and then we'll compare notes next time we get together. How about that?
Okay. Yeah, I would say if I'm 6 feet above the surface of the Earth and the object is 10 feet tall, it needs to go like 3.1 miles, maybe 3.2 miles before it dips beneath the it's gone so far over the curve that I can't
let's say
see.
like 10 miles, would you say would be like a safe distance that it would be completely out of your sight?
Oh, absolutely. If it were 10 feet tall and I'm 6 feet tall and it's 10 miles away from me, yes, I would not be able to see it.
Okay.
Light would need to be refracting in order for me to see it. We would need some serious refraction.
Yeah. All right then, man. Well, how about we end this and you can address your chat room?
Sure.
They've been really
guess,
cool, by the way. You guys in the chat, you guys have all been very civil. Thank you very much. I like the fact that the whole time I wasn't reading just a bunch of bullshit comments, dude. That's invaluable at this day and age, Jeff, especially online.
I will admit I wasn't tracking the chat too closely. I did see a couple insults and remarks, and I didn't address them then because I didn't want to bring attention to them and I didn't want to derail. But yeah, I'd like to thank the audience for their participation, for the things that they brought to my attention, and hopefully they were having a nice civil conversation among themselves. The last comment I do want to make to you specifically, Josh, is I don't think I would say to somebody that they just don't know how big the Earth is. I think what I would say to them is it's hard to grasp the scale of how big the Earth is. Because like it's 2,500 miles or so from New York to Los Angeles, maybe like 2,600 or so, but like New York to Los Angeles is about 2,500 miles. Okay. So you would need to go from New York to Los Angeles and back 5 times in order to get the same value as the rough circumference of the Earth. Okay.
Yep.
Those are values I can understand. I can understand that. Like, okay, I know how big the Earth is. But I still don't, on a regular basis, grasp that scale. Because when am I dealing with distances of 25,000 miles? The distances I deal with on a regular basis are like, it's 16 miles between my home and my office. Like, and it's 60 miles from my home to my in-laws, and it's about
I was kind of
50
thinking
miles.
I just got rid of a car that had like 130,000 miles on it, right? And I was thinking one day, I go, I've driven around the world like 6 times. Like,
yeah. See, like, and I mean that kind of helps. Like when you think in the grand scheme of things, like, wow, I've driven around. I've done the equivalent of driving around the Earth this many times. And how long did it take you to do it?
About a year. Well, no, I take that back.
If you did 130,000 miles in a year, I have no idea what you were doing.
I drive for Uber, bro.
Yeah, but I do like 12,000 miles a year.
I'll give you an example, Jeff. I just got a brand new 2017 car in like December 27th, I think I bought it, right? Like 2-3 days after Christmas.
Mm-hmm.
It's got 9,800 miles on it, bro.
I have 65. Yeah. Because I also bought a car very shortly after Christmas because my car was totaled very shortly after Christmas. So I had to buy a new one. Good times.
Yep.
But yeah.
But all right, so
yeah, and so sorry, I keep coming up with one more thing to say. I really am tired. I'm really going to go to bed after this. But since I brought up the topic of scale, and you can take this or leave this because I'm going to be talking about something you probably don't believe, but the number of inches in a mile, inches per mile, is 63,360, okay? 63,360 inches in a mile. That value happens to be very close to the number of astronomical units per light year. An astronomical unit is about 93 million miles. Okay? So if you ever wanted to make a scaled version of the Earth, the Sun, and the next closest star, the distance between the Earth and the Sun would be 1 inch. And the distance between the Sun and Alpha Centauri would be about 4 1/3 miles away. That's a way that I can understand the scale of the universe as physics explains it to us today. Because I cannot fathom 4.3 light years. I have no concept of what that is. But I do know how big an inch is, especially an inch in comparison to a mile. And so for me to say, if the distance from the Earth to the Sun is 1 inch, then it's another 4 1/3 miles to the next star. That's how I can grasp the scale of the universe, because they're huge numbers. They really are. And so with that, I do want to end it. I'm winding down. I'm going to pass out at my computer.
Thanks a lot for that. Actually, that's something cool to actually think about. The fact that basically, essentially, 1 light year is pretty much from here to what they tell us is from here to the Sun.
No. It's 1 astronomical unit is from the Earth to the Sun.
Unit, my bad.
Yeah, like it's basically our way of being so Earth-centric. Like we're going to name a unit after the distance from the Earth to the Sun.
Well, what do you expect when the whole reason why a foot is 12 inches is because it was the size of a king's foot?
Yeah, that's why I prefer metric for like all these physics things. But honestly, like I use the imperial system in my daily life. I know how many miles it is to my office. And I could tell you an easy way to convert from miles to kilometers, but I really want to go to bed.
Yeah. All right. Good night, man. Peace out.
All right. Good night, Josh.
See you later, bro.
See ya. All right. So, chat. Let me not ignore you. Again, I want to thank you all for being here and participating. So, Ben Delight. It's a great way to easily figure out the scale of light year distances. Yes, it is. I was so pleased when I found that out, that the ratio of inch to mile is pretty much, it's like 99.6% of the ratio of astronomical units to light years. It really helps me grasp the scale of the galaxy. The other thing I found out, that other thing that I didn't tell Josh just now, in order to go from miles to kilometers, that ratio is almost exactly phi. It's almost exactly the golden ratio. So if you know your Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, 21, 34, etc., all you need to do to go from miles to kilometers is treat your miles number as if it's a Fibonacci number and go to the next Fibonacci number, and that's the number of kilometers. So for example, if it's 21 miles from A to B, then it's about 34 kilometers from A to B. So if it's 7 miles from A to B, 7 is 1/3 of 21. So what's 1/3 of 34? That's 11 and a little bit more. So 7 miles is a little over 11 kilometers. So that's the little miles to kilometers trick. And it goes the other way. If you know the kilometers and you need to get miles, you just make the kilometers a Fibonacci value, and then you go one number before, and that's your miles value. And if Uber was listening to the YouTube video, he heard it. Spoiler alert. I guess I won't talk about it next time. So let's see. Let's quickly give a shout out to everybody who is here tonight in chat. Beach 8, Brain Grunt, Dave Hinkle, Jonathan Doherty, Sue Lynch, Charlie, 3 Moire. I don't know if that's how you pronounce your name, but that's how I pronounce your name. Builder 102. And that's as far back as I was able to scroll. And of course, thank you again to Josh. Again, it was a good night. I'm glad we were, oh, and One Big Pond, how can I forget you? Yeah, so again, I'm glad we were able to have this civil, polite, calm conversation for 2 hours now. So it was great. Thank you all. We'll do this again sometime. Have a good night or a good morning. If I stay up any longer, I'm going to have a good morning or a bad morning. So good night, everybody.